This KL7AJI, and want to thank him for volunteering. He's a prolific author, has written for many of the ham magazines we read. Um, I happened to see his presentation at the Ham Expo recently, and that was what led me to contact him and ask him to speak tonight. He's going to talk about Solar Cycle 25 and how the ionosphere works. And I think you'll enjoy the talk very much. Obviously, this is something that's covered on our tests, as well as the fact if you want to be successful on the air, it helps to know something about this subject. So hope everyone will get something out of it this evening. Anthony, if you haven't already, you can turn on the recorder.
Okay, I turned on the recorder. I'm going to go ahead and mute everyone. So Eric, you'll need to turn yourself back on. I'm going to make you a host so you can share your screen.
Alrighty. Okay, I'm demuted, I guess. My audio good?
Yes, just give me 1 second. I'm going to make you a host, and you should be able to share your screen if you need to.
Alrighty.
Everything looks good. Thank you.
All right. Well, my name is Eric Nichols. Here's my QSL card here, KL7 Alpha Juliet. Been licensed since 1972 and had my amateur extra KL7AJ since 1977. So I've been at this a little while. And most of the material I have is going to be from this book, Radio Propagation and Radio Science, published by Ada Borel back, what year was this? A couple of years ago. And this was actually my kind of my second in the series here, 2015. Okay, well, when I was asked to talk about Solar Cycle 25, I was rather daunted because that requires doing some prognostication, and we don't have a clue what's happening. I'll have to be honest, we don't know what's happening with 25 at all. However, what I would like to do is present, whenever you're talking about any scientific phenomenon like the ionosphere, we talk about the normal first, and then we talk about the oddball and the phenomenal, and which is kind of the season we're in right now. Now, not only is this an oddball sunspot cycle, at least beginning, but we're also in a very odd place here in Alaska. In Alaska, we're kind of the Bermuda Triangle of RF.
Amen. Amen.
Now, this is not true of all of Alaska. We are underneath the auroral oval here. Some of us call it the auroral sphincter, but it's a very highly absorptive area of interior Alaska. And if you've ever seen any overhead shots of the aurora from the space shuttle here, we're right in the center of that thing. So if you're south of the auroral oval in what we call the tropics of Alaska, down in Anchorage, it's a whole different planet down there. So they actually have some propagation that's a little more normal than what we have here. But in general, what I'd like to do is talk about basically how the ionosphere works under normal conditions. Then we'll talk about later, after we establish how it's supposed to work, we'll talk a little bit about how it actually does work. So here's some numbers to consider. And when we go through this, if you aren't amazed that the ionosphere works at all, you should be. Now, can you see this blue and green arc here pretty well here? Here's the surface of the Earth here. And
Yes.
We want to give you some idea of the proportions that we're talking about. The breathable atmosphere is up to around 10 miles, and up here, where things get interesting to us, is between 450 miles and a little bit higher. It actually goes into deep space if you want to consider where the ionosphere actually ends. But to give you a little perspective here, the density of the ionosphere where things are of interest to radio is approximately a quadrillionth of the density of the ionosphere or of the air at ground level. So there isn't much material up there. As a matter of fact, our good friends at ISCAT in Tromsø, Norway, has a big ionosphere heating facility, very much like HAARP. They calculated the entire mass of the ionosphere, and it comes out to be a little more than a metric ton. Put that in perspective, if you compress the entire ionosphere into a tank, you could put it on a hand truck and scoot it into the corner of your garage. So it gives you an idea that we aren't really working with very much up there. And the fact that there's so little there to work with, the fact that it gets flaky at the time should not be surprising at all. It's a very, how shall we call it, gossamer or ethereal substance that we're working at. Well, let's talk about what the ionosphere is actually made of and how it works. So what's most of the atmosphere that we breathe here at ground level?
Nitrogen.
Nitrogen, okay. So nothing's really changes that much. As a matter of fact, the proportion of the different gases that we have in the ionosphere are pretty much the same. It's just they get an awful lot thicker or thinner as we get up. So we have this very thin region here, and by thin I don't mean it's sparse. I mean it's very dense, but also a very thin shell, where we experience normal stuff like tropospheric propagation or anything like that. And then we have several hundred miles up here, we have the ionosphere that's of interest to us, and especially the F layer. Now the D and E layers are actually down closer to like 90 miles. But when we're talking about F layer propagation, since most of us, I think here, are primarily DXers and contesters and HF operation folks, we'll talk more about that. So the process of reflecting a radio signal is somewhat misnamed. We call it reflection, but it really isn't reflection. It's actually absorption and re-radiation. So again, I'm a very Socratic teacher here, so I would expect a lot of feedback here. Who can tell me what creates a radio wave to start with? How do we generate a radio wave? Anybody?
Electromagnetically.
Okay, now what's the main ingredient for generating an electromagnetic wave? A charged particle. So what type of charged particles are we primarily working with in the ionosphere? A little hint.
Electrons.
The electrons. The electrons are actually the main ingredient that we work with. Now, I'll give you a perspective here. What's the relative? Let's take a proton. A proton is the simplest ion, a hydrogen ion, we could call it. What's the approximate ratio of weights of or masses of an electron compared to a proton? In other words, how much more does an electron, or how much more does a proton weigh than an electron?
About 1,800 times.
That's about right. Yeah, we can round it off to 2,000 miles. Now, we aren't working with free protons most of the time. We're working with nitrogen primarily. We also have some oxygen, but the rare earths and that sort of thing really don't have much effect on radio propagation that we're concerned with. However, let's pretty much confine our talk to nitrogen. So what's the atomic number of nitrogen?
It's 7?
7, very good, okay. So that means that if we're primarily working with nitrogen, now we know that nitrogen is in its normal state, it's actually an N2 molecule. You don't really have a bunch of free single nitrogen atoms. So we basically work with N2 molecules because nitrogen likes glomming onto another nitrogen. So that means that the lightest ion that we work with is going to be 7 times 2,000 or 28, two times atomic number 7. So that's 14. And that 14 is 2,000 times lighter than, or heavier than an electron. So basically a ionized nitrogen ion is going to be 28,000 times as massive as an electron. So what's going to respond faster to an electromagnetic signal passing through? Well, the electron, of course. Okay, the electron and the single ion have exactly the same charge, but the ion has 14,000 times as much mass. So we have this interesting situation where we have the electrons are they're available for accelerating, and to create a radio wave, we have to accelerate a charged particle. The electron's much easier to accelerate, so they're going to have much more effect on the propagation than the ions themselves. So anyway, what we want, if we want an ionosphere that's going to be working well, we want a lot of free electrons. Now, where do the electrons come from? Anybody?
Ionized gas.
Okay, basically it's ionized nitrogen. They're slapped off of the nitrogen molecules we have there. So what's the primary motive for slapping electrons off of nitrogen?
Hard ultraviolet.
Ultraviolet, right. So now we're finally getting some connection between the ionosphere and the sun. So ultraviolet primarily comes from the sun. There are some other sources, lightning storms, that sort of thing, can actually activate the E layer and D layer quite actively. But most of the UV that we're interested in comes from the sun. Now, we know that we have a lot of ultraviolet from the sun when we have a lot of sunspots. But a lot of people think, well, the sunspots are creating the ultraviolet. No, they really aren't. The sunspots are an indicator. They aren't a prime mover. And how do we know this? Well, we know that because if we have a lot of sunspots, even if they aren't in the right place to aim at us, it still is generally going to give us good propagation. We're going to have good ionization happening because the sun itself actually is pretty uniform in terms of its illumination and its generation of ultraviolet rays. It pretty much emits all those, what we call an isotropic radiator. The sunspots are an indicator that there's a lot of magnetic activity and we're going to have a lot of ionization potential. But the sunspots themselves do not cause the ionization. So keep that in mind. Now, one case where the location of sunspots can be a significant factor is like the coronal mass ejection we had last week when the sun actually blows chunks. And when the sun blows chunks, if you're in the way of where that chunk is being blown, you're going to have all sorts of nice auroras, but horrible radio propagation. So we have two things happening. So we don't want the sun blowing chunks. What we want is a smooth bathing of ultraviolet radiation. And this is what occurs in the 11-year sunspot cycles, or whatever, however many years we have on this last one. This is, it's been on for like 14 years since the last peak, they think. So we have a very erratic solar cycle right now, and it's not absolutely certain that we're into the next one yet. There's still some hangers on from the 24th cycle. But assuming that things are working relatively normal, we are at the very beginning of the 25th sunspot cycle. Was any old timers here around during the cycle 19? Oh, I see all the gray here. I thought somebody would have been. I missed cycle 19 by just a few years. But that was an absolutely phenomenal cycle.
What years was that?
Well, it peaked out at 1958. So that was when you could talk around the world day and night on 10 meters.
Yeah, it was close to that.
Yeah, very close to that. So anyway, we have not seen anything close to that. And as far as predicting what this cycle is going to be, I'm not a prognosticator. But we simply have to watch what's happening. But again, I'm going to talk mainly about what's normal and what we can expect under normal propagation, with the proviso that cycle 25 we don't know if it's normal or not. So anyway, we have solar rays coming in here, ionizing lots of free electrons, and these free electrons are free. What do we mean by free? Well, they have been slapped out of their ions. So we know that electrons are very, very light. And what do we know about how does an electron respond to another electron?
Runs away.
It repels each other, okay? So even if we have all this ultraviolet coming in here, it's labeled as UV, coming here and ionizing all this stuff, we have all these huge numbers of electrons that are free. Why don't they go blorping off into space? Because if they blorp off into space, they aren't going to do us any good. We want electrons where they can do us some good. So what keeps the electrons where they're supposed to be? Any guesses?
Gravity?
No, actually, gravity is so small for an electron that it actually has almost no effect on it. But where do the electrons come from?
The ion or the nitrogen molecules.
Right, they were knocked out of the nitrogen. So now we have all these nitrogen ions all over the place. Now, what keeps these? We know that since these are also positive, they're the same charge, they're also going to want to repel each other, okay? But what stops the nitrogen ions from warping off into space?
Attraction to the electrons?
Nope, it's actually, in this case, it is gravity. remember the nitrogen ion is 28,000 times the mass of an electron. So the ions actually are kept in place by gravity, just like free air is. So as far as the gravitational attraction, it's not much different than unionized air. So we have these two really neat things working. We have these layers of nitrogen, which are, you know, just because of the differential in pressure as we move up higher, we have the nitrogen ions in kind of a layer. And then the nitrogen ions are, how should I say, they're loosely bound to the electrons that were slapped out of them. So we have this massive kind of a buffer or a container of nitrogen, which keeps the electrons in order. I like to use the example of some very large person with a very small dog on the end of a leash there. And the dog has a certain degree of freedom, but he always has to return to his master who's got the most of the mass there. So the massive ions up there are what keep the electrons in pretty much an order, what we call a layer. Now, you don't want to get the impression that we have any region of space that's nothing but free electrons or nothing but ions. There's actually a soup there of various concentration of electrons and ions. And so what we want to look at is where the most concentration of these electrons are going to be. So what we can do here, we can go to, let's pick an ionogram here. Let's see here. Can I do a search on my files? Here we go. I'm going to do something different here. I'm going to actually go online and find our latest ionosonde, our local ionosonde here. How many here work or check out your ionosondes regularly? Well, this is pretty typical for up here. Everybody see this okay?
Mm-hmm. Yeah.
Okay, this is a typical ionogram. Now it's not very good here. I'll go back maybe a month or so and find a decent one. This is taken from the Eielson Air Force Base ionosonde. It's called a Digisonde. Lowell Digisonde, this company here, has a huge network of ionosondes all around the world there that actually probe the ionosphere. They send a radio signal up, and what they do is they look for the return time of the radio signal. Unlike all the solar indices that everybody gets obsessed about, the ionosonde does not lie. It tells you what it is in real time. The solar indices will tell you what the ionosphere is supposed to be and what it should be, but also paints with a very broad brush. Now, how many know that your ionosphere is not the same as my ionosphere? Going by solar indices is going to tell you, is going to put a very broad brush on things and say, well, we got good propagation here, it's got to be good same everywhere. No, the ionosonde is the tool of choice because it tells you what the propagation is going to be where you're at. So there is a list here. Let me go to the, let's see, Lowell Digisonde station list. And feel free to, again, interrupt me at any time and fill in any gaps you need here. Station list, Lowell Digisonde. Now, Lowell is not the only place that makes Digisondes, or makes ionosondes, but the Lowell Digisonde is pretty much the standard of the industry, and they have a huge network around there. You guys are all in Ohio, and let's see, let me find the closest ionosonde to you guys. Let's see. Let's sort here. USA, Eielson Air Force Base, Colorado Springs. Let's see. You guys are probably closer to Millstone Hill than you are to Colorado Springs. Right?
The one in Michigan, the Alpena, Michigan, up near the top of the screen. That's probably the closest one to us.
Oh, okay, let me grab that. Okay. There we go. See what is happening today. We actually have some 20-meter propagation today, so it might even be better for you. So here's the latest one. These are done in 15-minute increments. Oh, wonderful. You guys have
Yes.
an amazing propagation there. Okay, so anyway, let's talk about this ionogram a little bit and talk about how to read it. You can read an ionogram. It's a lot less frustrating than trying to interpret solar images. So what we have here across, everybody see this okay?
Yes.
Okay, what we have across here is frequencies in megahertz, and up here is distance in kilometers. So what we do here is, an ionoson is simply an upward-looking radar. It uses what we call NVIS, or it's not NVIS, it's true VIS, vertical incident sounding, sends a short pulse up to the ionosphere and looks for a reflection coming down. And we sweep the frequency here. So about every 15 minutes, now each side can be adjusted to give more or less frequency in terms of sounding. But what we have here is pretty typical. We have red traces here, and you see we have actually multiple traces. Why would we have, looking at just the red here, why would you have a trace here and a trace here and a trace here? Any guesses?
Oh, refractions from the ground.
That's right, multiple reflections, okay? So we're most interested in this lower one here. All these up here can be pretty much ignored. There's actually a fourth reflection up here, very faint. So what we have here is this black line is what's called the electron density profile. And this tells you the height at which you have a maximum number of free electrons. So if we go to this cusp over here, and this is pretty typical, we have the most number of free electrons, about 250 kilometers. So this is where we're going to be most interested in looking in terms of long distance propagation. There's a whole pile of information in here. The first most important parameter we have is what's called the critical frequency. It's the F2 layer critical frequency. And in this case is 5.538 megahertz. Now, anybody here work NVIS propagation? Anybody do any local emergency communications with NVIS?
Yes.
Yes.
Okay, typically if you're working in, excuse me, NVIS, you want to be about 10% lower than the critical frequency here. So this would actually be pretty good propagation for 80 meters, maybe 60 meters, kind of on the verges, on the edge for 60 meters. So what happens here, if we just look at this curve here, as we increase the frequency, we see that the reflection height increases. So just before the critical frequency, we have a maximum reflection height. So at this point here, we have almost 600 kilometers of height. Now, what's the advantage of having a very high reflection?
Longer skip.
Longer skip, right. So a skip down here is pretty low, pretty short, and then as we move up, we get longer and longer skip. Now again, keep in mind that these curves are only for NVIS propagation. If we look at low angle propagation, we look down here at what's called the MUF, maximum usable frequency, and this D is the distance to the first skip. And so as we lower our launch angle, as we get closer and closer to the horizon, we see that our maximum usable frequency goes way up. So again, this critical frequency is the worst case scenario. It's for NVIS propagation. As we move, as we aim our signal lower, why we want, this shows you why we want very low angles. If we can achieve it, not only do we have longer skip distances here, but we also have a higher maximum usable frequency. So even though the critical frequency here is only 5 megahertz at low angles here, we're up in 17 meters almost. Okay, that making sense so far? So we have a lot of these other parameters here as well. We have, let's see, we have the thickness of the ionosphere. The ionosphere, as I mentioned, is even though there isn't much material there, it covers a huge amount of space here. So the difference between like F2 and HF here is about 225 miles. So that's the actual thickness of the ionosphere that we're getting reflections from. We can also measure between virtual height and true height. Can anybody tell me what the difference between true and virtual height is of an ion of a reflected signal? Okay, what's the speed of light, or what's the speed of radio in free space?
186,000 plus miles an hour.
Right. What's the speed of radio in the ionosphere?
Well, it's got to be lower than that. I'm not sure exactly what.
It's lower, but not only that, it continually changes the speed of propagation as you move up. So what happens is as a radio signal is moving up into the ionosphere, it slows down and down and down, and finally, when the electric and the magnetic fields reverse, basically it's not moving at all, and then it's reflected at that point, and then it's regenerated, and then it comes back and accelerates faster. So because there's a high change of speed on here, we have to use what we call the virtual height, which accounts for the change of the velocity there. So it isn't like radar in free space where you can tell exactly how far something is by the delay time itself. Since our propagation speed is always changing, we're going to have some very different readings between the virtual height and the real height. And if we like, here's our virtual height here, 246 miles, and here's our true height here. So you see, it can be a radical difference between the true height and virtual. Now, for most of us, we don't really care what the true height is. We're just looking at what altitudes does it seem like the radio signal's reflecting from. So we use what's called the virtual height, was actually what we call the height of the ionosphere is actually the vertical height there. So now we get to my interesting thing, and this is where I have kind of dwelled on for many years here. Can anybody tell me what the difference between the red and the green traces is, or are?
One's the ordinary and the other's the extraordinary wave.
Very good, very good. And did you know that from my book, or did you know that before?
From your book.
Okay, this is something that's not very well known by most radio amateurs, but when you send a linearly polarized signal into the ionosphere, it splits into two rays. One is clockwise circular polarized, and the other is counterclockwise circularly polarized. The red is what's called the ordinary wave, and that is clockwise in the northern magnetic hemisphere. The green is counterclockwise in the northern magnetic hemisphere. Now, one thing that this shows that doesn't give you a complete picture, this is simply shows you the difference in reflection height for the X and the O rays. It doesn't tell you the divergence in the azimuth. The X and the O rays can diverge by as much as 180 degrees, especially if you're right near the magnetic pole up here. So what does that tell you? Well, it tells you a lot of things. First of all, how many here are using circular polarization on HF? Maybe 1 out of 10,000 hams, okay? It has not been explored much at all. But every time you launch a radio signal in here, you actually have these two rays, and they can diverge by huge amounts. Basically, the O mode pretty much follows great circle paths. So if you want to know where to steer an antenna there, you can go by the O mode and say, okay, that's pretty much where we want to aim our antenna. The X mode, all bets are off, because the X mode tends to follow magnetic field lines. So has anybody here worked with a program called PropLab Pro 3? It's developed by NL7WS. He writes a regular propagation program column in CQ magazine. It's a wonderful program. It's the only program readily available for hams that actually shows true ray tracing. And it will actually show you, if you pick 2 points on the planet that you want to talk between, it will show you the actual path that it takes for both the X and the O mode. And they can be very, very different. So what does that tell you? Well, how do we separate between the X and the O mode? The only way you can do that is with a circularly polarized antenna. Now, if you do have one of these beasties, what you can do is you can tell what path it's taking if you know which mode it is. So you first of all use your circular polarization to tell whether it's clockwise or counterclockwise. And then we can use a program like PropLab Pro 3 or whatever, and then determine, okay, which one should we focus on? Should we be circularly polarized or clockwise or counterclockwise? And because nobody pays attention to these, and the reason you can get by without knowing anything about this is a linearly polarized antenna, a dipole or a Yagi, whatever, doesn't care. It responds to both clockwise and counterclockwise signals the same. Now, if you do have a matched circularly polarized antenna to the wave, you get 3 dB of gain over what you'd have with a dipole. So you can actually get a little bit of gain by using circular polarization. Now, on the low HF bands, obviously a circularly polarized antenna is quite a large beastie. They do use up a lot of sky. So this is one reason why we don't see a lot of this being used on HF. But it's some fascinating science there. And if you, one of the things that we do, for example, if you're working with somebody over the pole and you say, oh, I steer my antenna for the strongest received signal at my location, and then I make the assumption that my antenna is oriented in the right direction for the guy across the pole at his QTH. Well, this may or may not be the case. If I'm talking to him on the X mode and he doesn't know it, it could be that I could be 90 degrees off from the optimal. So the only way you can know if you're steered in the right direction is to ask the other station, you know, do some steering and ask them, is my signal getting better or worse as I'm steering this? So not only can the X and O be very radically different, they can be skewed quite a bit in the horizontal, not only vertically, but because the magnetic field lines in the Earth have both declination and inclination, the X mode can follow them around as well. So the great circle paths are almost meaningless for the X mode. Now, has anybody ever actually discovered something or experienced something that looks like you might have a conflict with X and O mode? Has anybody ever operated in real high latitudes? Anybody here worked in Alaska at all? Okay. It's weird. If you've come up here, sometimes you'll hear a signal coming over the pole, and you'll have, like, let's say a pretty good high gain 3-element monoband antenna, 20 meters. And there are times when you can steer this antenna clear around the azimuth and it makes no difference at all in the signal strength coming in. So what conditions would cause that to be? How can that be? Can somebody give maybe a brief description of the geometry that would cause that to happen? Well, one of the things that we have here, when you have a large magnetic field, is the ionosphere is no longer horizontal. The ionosphere can be tilted, and over Fairbanks, the ionosphere is tilted about 90 degrees, 60 degrees. So if we're bouncing a signal off a tilted surface, kind of all bets are off. You know, for example, let's say we have a low angle propagation from the lower 48 coming toward Alaska. It's bouncing off this highly tilted ionosphere, and it could be coming straight down. Everybody see the geometry, how that works?
Yes.
So we have a signal that's coming straight down from the ionosphere. And not only that, but it's also going to be circularly polarized. Well, how much discrimination of circular polarization does a Yagi have for a signal arriving broadside? I'm not talking about from the front, but coming from straight overhead. Zero.
It's no longer a Yagi at that point.
It's no longer a Yagi. It's no longer can discriminate. So what happens is a lot of times when we see that, that's what's happening is we're seeing an angle that's been launched at a low angle, bouncing off our tilted ionosphere, coming straight down, and then we have no way of steering it. So very interesting phenomenon. And until you've actually experienced it, most people don't believe it. So we are in a different planet up here. Now, everything that we see on this ionoson here is duplicated on the south pole. Now, we really don't have many ionosons on the below the equator, but let's look at something that's very near the equator. So let's go to Picamarca, Peru. through. Mark out of this thing out of the way. Oh, it does. Okay. And we'll see if they got any propagation. Okay, so this is pretty typical there. Yeah. Now you see they have an X and an O ray here, but see they're almost right on top of each other. And the reason they're right on top of each other is the magnetic field line is pretty much neutral at that point. So the differentiation between the X and the O mode is not very much. Let's see, we can go back a couple of previous ones. Oh, that's interesting. Can anybody maybe hazard a guess as to why this thing's all spread like that? Rather than be a nice, well-defined, thin line. Anybody? Well, that's Doppler shift. The ionosphere is not stationary. It can move, and it can move fast. Many years ago, we built a Doppler ionosonde here at High Pass Observatory, which is kind of the predecessor to HARP. And we were able to actually observe the ionosphere retreating at 700 meters per second right at sundown. So you have all this Doppler shift built into there. And the ionosonde is designed to actually show you a color shift to correspond with the Doppler shift. So we have the red shift and the green shift, or red shift and the blue shift. And as you see here, things can change pretty rapidly. I only went back about an hour and a half and the ionosphere is gone. Okay. So, you know, your solar indices won't tell you this kind of stuff, you know. So when we see things rapidly change like that, let's go back up to, let's see, a little closer. Let's go to HARP ionosonde.
Eric, I had a quick question while you're, when you're choosing an ion node to look at, is it better to find something that's equal in latitude if you can't find anything really close?
That is correct. Yes.
So Mill Hill would probably be better for us than
Yeah.
Alpena.
And again, remember the readouts that you get from these are only for the first top. So again, the ionosphere can change pretty rapidly between one location and another. So you kind of almost have to interpolate what's in between, you know. So the ionosondes are not, how should I say, equally distributed around the world. You know, some with quite a few that are pretty close together, and then you know some huge gaps in coverage here. But they're putting more on the air all the time. Well, you see, we're pretty dismal up here. Moving back here, we have almost nothing happening. Actually, I wonder if I could show the.
If I understood what you said earlier correctly, if I was up where you are, I would do well to have a rotor like I have on my satellite antenna. Would that actually be helpful? I realize you probably
Yes, it
can't
would.
do that with a beam. It's too big, but
Yeah, you wouldn't really need a rotor, but you want to be able to at least switch between right and left hand. So you have a cross-polarized Yagi, and a switch with a 90-degree phase will give you a switch between right and left. Now, one way you can actually experiment with receiving C-pole signals here, very effective antenna, especially on low bands, you know, 40 and 20 meters. Is just a pair of crossed inverted V's. All you need is a single pole in the middle, and then you set up two inverted V's at 90 degrees, and then you feed them 90 degrees apart. So what you do is you just take put a T in there between them, and one length of coax will be 90. So then you can swap between right and left polarization by just changing the connection between your two antennas there. And so that's one thing that we did an awful lot at High Pass. We had we actually had some broadband phase shifters that did that for us. But you can quite typically, even with a very haphazardly erected C-pole antenna, you can typically see a 3S unit difference between being the right polarization and the wrong sense. And this is really easy to test with WWV. So 15 megahertz especially. So if you build up a cross-polarized inverted V, tune it to 15 megahertz and switch between right and left circular polarization, it'll be a dramatic difference. This is one thing that just really surprises hams when they first experience that. So as we can see, with some very simple technology, and it's not really high tech at all, it's just properly using what's been known in the ionosphere for a long time. Now, I wish I could take credit for this whole X and O thing. X and O propagation has been known since at least the 1940s in terms of the ionosphere. However, there was a 70-year gap in ARRL publication between when that article was published in 1940 and I wrote my article in 2010 called Give Me an X, Give Me an O, What's That Spell Radio? And so there's a 90-year gap of zero information, at least in the ham literature, on X and O propagation. And what's interesting, the extraordinary and ordinary modes were known in optics. Isaac Newton probably approached pretty close to understanding that. So ham, or I shouldn't say, scientists have worked with optics a lot longer than they have with radio, because well, the reason is we have sense organs that detect light, where we don't have any sense organs that works with HF very well. So, but all the phenomenon that we see in the ionosphere can be exactly reproduced in optics, and that's pretty amazing. We have very, very consistent universe. Oh, any questions right now?
I just had a question. Some of the ion node sites have moving patterns. I'm guessing they just interpolate between each of the sets of readings. Does that tell you anything in the movement, or other than?
Yes, it does. And this is what I talk about the Doppler ionoson. There is Doppler actually built into these. If we look at this chart here, see the scale over here, where I got my arrow?
Yes.
Okay. This is actually the green. The green is, well, I should say, we have red shift and blue shift, just like you do in light. So if the ionosphere is coming toward you, the frequency is going to increase, so it's going to be shifted toward the blue. And as it's moving away, it's going to be shifted toward the red. And we can see that on some of the plots here. These are kind of random here. Let me see if I can find one where it's very clear. I may have to go back a few months to find the, let me go back. Yeah, well, let's go back a year. Maybe we can find some good Doppler shift here. Now that is not good.
That's to go back to bed.
This is what Alaska, interior Alaska is like most of the time. So I wonder, why do I even have a radio?
Yeah, does that chart say take up another hobby on it?
That's right, exactly. Well, let me see. Let me go back. When was a good year? Trying to find a good year. Yeah, let's try this middle of summer here. Maybe you can find something in some sort of during the daytime here. Oh, here, beautiful. Okay. See all that blue there? On that trace there, and see how smeared out that is? That's Doppler shift there. So this blue side is the ionosphere is coming toward you. And by the way, interestingly enough, the ionosphere can be both advancing and retreating. Anybody seen photographs of the aurora, visible aurora? Have a thing called curtaining. So imagine grabbing a hold of a carpet and giving a big flap, and you have a wave that propagates. Some of that's moving up and some of it's moving down. And that's almost for certain what's happening here. We're looking at a part of the region of the ionosphere that's moving up, and part of it that's moving down at the same time. So the beam of these ionosons are not super narrow. You got moderate gain, but they can cover a pretty good chunk of sky. So as the aurora is moving around and flapping around here, we're seeing the results of that. Let's go back a few years. Okay, we can see. Usually this is pretty close to sundown is when you start seeing this, because that's when the the ionosphere starts retreating. Now you see in general, let's see, maybe I'll go a little later. Maybe you can see how the ionosphere in general after sundown starts retreating overall. Now, when the ionosphere retreats, it always retreats from the bottom up. So this is why why bands go long, right? We have very thick ionosphere, but it gets thinner from the bottom up. So what happens is the main core of the ionosphere that's doing the reflection is moving up higher and higher as you get later in the evening. And it takes a lot longer to de-ionize than it takes to ionize in the first place. So the maximum ionization theoretically takes place at high noon, but it doesn't always. So here we see it, we're moving, some of the blue is moving toward the green here, which means the acceleration is not as much as it was in the past here. So anyway, let's see. Yeah, we're getting a little more stable ionosphere here. We're seeing some better defined X and O modes without as much Doppler smearing. There's a lot of fascinating stuff. I mean, I've been playing around with the ionosonts for forever. So here we have a triple reflection. Now let's see. Can anybody tell me when the last really good sporadic E season was?
Last summer.
January?
Last summer was a good one?
Yeah.
There was some in January, wasn't there?
Last May, actually.
Okay. Let's go back a year.
I would say IA or UHF World Championship weekend was the best of the year.
Okay. Let's see what we got here. I'm just starting to see some maybe. Now it's called sporadic because it's sporadic, right? Okay, we're getting there. See this down here?
Yes.
That's sporadic E. Now, how do we know it's sporadic E? Other than the fact it's in the E level, that's a good indication. It's down here at 80 kilometers as opposed to 250 there. What's another good indication that it's sporadic E? Well, it's relatively frequency independent. See, it's a straight horizontal line for most part, whereas F1 and F2 layers are frequency dependent. The F1 and F2 layers are very what we call dispersive, refractive, whereas sporadic E can be very much like a specular reflection. And why is that? Oh, beautiful. Here's beautiful sporadic E. Now this is a second reflection here. Let me go a little further. Maybe things are building up here. Oh, what beautiful. Here's beautiful sporadic E here. I mean, this is textbook quality. See that? See how nice and straight across that is? Everybody see that?
Mm-hmm.
Now, see, it's not frequency dependent like the F layer, so it's straight across. Now, why is that? Why do we have not a frequency curve like we do with the F layer? Well, sporadic E is primarily caused by groups of large clusters of free electrons, but they are not mixed in with a bunch of ions. Unlike the F2 layer where we show the electron density profile where you have this mixture of electrons and ions. The E layer is almost nothing but electrons. And how does that happen? Well, if you look at the source of E layer, well, let's go back. The F layer, the electrons come from the ions that they got slapped out of. So we're pretty much going to have an equal number of electrons as ions in the F layer. Whereas E layer is a entirely different source. What we have is we have things like micrometeors coming in, ablating in the E and D layer, and creating huge gobs of free electrons. We also have lightning strokes. Lightning's probably one of the major sources of E layer. Sporadic E. Another source is stratospheric winds, wind shear. There's a great RSBG presentation on sporadic E. That's excellent. I forgot the gentleman's name, but the RSGB, they are really big into sporadic E in Europe there. So basically, we have a different source of electrons. They aren't ripped off of local ions like in the F layer. So what we have here is big clusters of free electrons, which are interspersed with neutrals. So rather than these electrons mixed in with ions, we have electrons mixed with neutrals. So because we no longer have the modifying effect, we said earlier that the F layer kind of keeps keeps tabs on the electrons. We don't have that action happening on sporadic E. The electrons will repel each other because there's no ions to keep them in check. So that is why it is sporadic. And you can have huge gobs of free electrons, but then again, they disperse very rapidly because there's no nearby ions to keep that check. Does that make a lot of sense?
Yes.
So I say it's amazing how everything happens to work together for to make this work. So anyway, yeah, going back a couple hours here, he said absolutely classical sporadic E. And see how not only is it low, but it's also very well defined. It's almost like a mirror. And as a matter of fact, it has a lot of similarities to some optical properties like tropoducting, that sort of thing. Now, this is still quite a bit higher than tropoducting, but it has a lot of the same optical properties. So we call specular reflection, which is almost mirror-like reflection here. Isn't that neat? That's just amazing. How many here work sporadic E?
I went back and looked at my log, and on 610, I had a whole day. I had a whole chunk of West Coast and Central State 6 meter contacts. So I'm sure that day was a lot of sporadic E.
Yeah. Do you have any other question here? Oh, you look like it was.
Sorry, no, just raising the hand to the question. Apologize.
So let's see. Well, let's just keep going back here since this seemed to be a really good season. See what else we can find happening here.
If you look at 610,
okay, on 2020.
yeah,
Okay. 210.
and I'm at
Now, your ionosphere is not mine. This
Yeah.
is this we saw up here, so it's going to be very radically different where you're at. But I just want to show you an example of what sporadic E can look like. I have no idea what that is. That looks like, oh, that's a weird one. Let me go back a few hours here. It's really neat too if you take like a movie maker program and you download all these ionograms and you make a movie out of it. You get to see how fast this stuff moves. You know, it's really neat to watch the in real time the ionosphere scooting around. One of the things that we have that we didn't have when I was first working with this at HiPass and HARP is reverse beacon networks and all these SDR radios all over the place. They're amazing. I mean, you can put that stuff together and you can make compile a lot of data from wide range and get a much better picture than we ever could have guessed there. So there's a concept called sky mapping where you actually take reflections from multiple different sites and you combine them together both in phase and amplitudes. So anybody familiar with synthetic aperture radar? This is something that can actually be done at HF, and you can actually get a 3D picture of the ionosphere by compiling a bunch of reflected data from multiple widely spaced sites here. Here's kind of unusual here, at least up here it is. See this double cusp here in the red? That's actually separation between the F1 and F2 layer. Now, most of the time recently, the F1 and F2 layers kind of combine into one, and we really don't see a well-defined difference between them. In this case, you actually do see that. So anybody want to hazard a guess as to what causes the difference between F1 and F2 layer? I haven't mentioned it too much. It's one of them's oxygen, one's nitrogen. We have two different species to work with. So actually, when you have enough ionization to actually ionize oxygen, which takes quite a bit more energy, we actually can get the F1 layer down here. Yeah, this is actually quite unusual to see this much well-defined F1 layer here. Here again, you see this cusp here. So this is F2 up here, and here's F1. And again, this electron density profile, it tells you where the maximum electrons are. Now, what's interesting about this electron density profile, see how it's dotted line up on the top and it's a solid line down below? This can be measured directly with an ionosonde up to the critical frequency. Anything above the frequency, we have no information about. So this has to be interpolated using some mathematics. The only way to see what's happening above the ionosphere, above the critical frequency or the critical height, as we call it, is with a topside ionosonde, and they're few and far between. They're usually on, there's a few satellites out there that have been kind of short term. There's no permanent satellites up there that are doing topside sounding. Also, quite a bit of rocketry has been done, especially here in Alaska. We've done quite a bit of topside sounding. But basically, we call this region the ignorosphere because basically we can't really directly look at what's happening there. Now, when we finally start doing some DX from the moon, we can start doing some MEM propagation. So we originate on the moon, and then we can bounce off the top side of the ionosphere, perhaps, right? So anyway, that's there. So let's see. Again, here's a critical frequency, 4.35, which is far below the MUF. So the MUF, again, it behooves you to use the lowest angle radiation you can, if you can. How many have stacked Yagis? Anybody know?
No, unfortunately not.
The stacked Yagis would really the way they take advantage of lower angle propagation. But fortunately, even an antenna that, let's say you have a typical launch angle of 30 degrees, there's going to be some radiation at 0 degrees, and there's going to be some quite a bit higher. We aren't shooting laser beams around. The sloppiness of a typical Yagi is actually to your advantage because you don't have to be aimed right down somebody's throat to be able to receive. So the fact that we get by with so much is largely due to the fact that our antennas are not very high gain antennas. Obviously, if we're running a microwave, your alignment has to be a whole lot closer. So we can get by with a whole lot on HF here. So, any questions so far? Anything I haven't discussed that you have questions about that I have not even touched on yet?
The D layer on these charts really doesn't show that much, correct?
Yeah, the D layer is not a well-defined layer. It's pretty much absorption. So you occasionally get some reflection on D layer, but D layer is kind of counterproductive. The D layer primarily works on 160 meters and broadcast, obviously, so broadcasting is probably is affected more by the D layer than anything else. So D layer is actually most of the time works against us. D layer is very highly absorptive during the daytime. And so we really can't take advantage of the D layer. The best thing we do is hope it goes away.
So I do have one question.
Yes.
So considering communication satellites in say 10 meters with some of the low Earth orbit immature satellites we've had, would the sporadic E prohibit us from being able to communicate with those when it comes out, or how do we deal with that?
Yeah, it's really interesting. If I could go back here, I'll have to find it. Did you notice when I had those really good shots of sporadic E, there was also F layers as well? Now you would think that the E layer being fully reflective would not even let a signal get up to the F layer. But it's not a perfect mirror. It's kind of kind of like a tinted window more than anything. So we actually have, even though we have strong sporadic E reflections, we can actually penetrate that quite a bit. So the answer would be on 10 meters, you probably still have some pretty good propagation. As a matter of fact, anybody here around during Oscar 2 or Oscar 1 era, 2 meters up and 10 meters down, and it seemed to work all the time, So yeah, in general, it would not be too disadvantageous when they're sporadic either. Again, we can use it, when there is high sporadic activity, 6 and 10 meters just come screaming to life. That answer?
Very good, thank you.
Okay. So let's see. Well, let's talk about low bands a little bit. Again, we mentioned that go down to 160 meters, and especially anybody work in 2,200 meters or 630?
Not yet.
Not yet. I played around with it a little bit. I haven't gotten really into it, but the delayer absorption is one place where you really want to avoid. So those are pretty much nighttime bands. Now, here's something that's very, very, very interesting. Is how do we measure the direction of arrival of a signal in the vertical? Now we all know how to steer a Yagi around, right, and figure out which compass angle is coming from. But if we want to determine the angle of arrival in the vertical plane, how do we do that? It's a bit of a challenge.
Well, if you switch antennas, that would be one possible way. If you went from an antenna that had a high takeoff angle to one that had a low takeoff angle and compared them.
That's a good one. Another one is if you know the general azimuth direction it's coming from, you can have one well in front of the other one, and then you can look at the phase difference between those, and that's interferometry. So that's a very, very common method used for not so much by hands, but scientific guys like doing that. Here's another real challenge to think about. One of the things that the driving force behind HAARP, everybody familiar with the HAARP antennas and the history of HAARP? Well, the whole idea of HAARP, the bottom line of HAARP was ELF communications for submarines. Now, pretty much those operate around 200 hertz. So really low frequency. You aren't talking about any high data rates. But what's really interesting is how do we talk about the near and far field of an antenna, right? So how do we normally know if we're in the near or far field of an antenna? And what's the difference? Why do we care? Well, let's say we're building a long boom Yagi, and we know that the Yagi works because we couple between each element. We're coupling the magnetic field of each antenna. So if we have a Yagi with, let's say 15 elements or so, and we remove half of the middle elements there, does the farthest front element have any effect on the radiation resistance of the driven element? No. Okay. No. So it's out of the near field. Now, how about the first director? Or how about the reflector? Are those in the near field?
Those would be in the near field.
Those would be in the near field. Now, what happens, interestingly, is we can actually extend where near field is. We do it by proxy. For example, you all work with transformers. You can take the output from one transformer, go to another transformer, go to another, and your final load is going to be affecting what you see. Well, same thing with an antenna. If we have a long boom Yagi, each element, even though the far end element is not in the near field of the driven element, if we have a bunch of elements in between, we extend our near field by doing that. Well, this creates an interesting problem in especially ELF communication. How do we know if we're in the near field or far field? Well, here's the next thing. How did HAARP generate ELF, or how does it? What does anybody have any history of how that worked? How would you efficiently generate an ELF signal in 200 hertz region?
Are they using audio frequencies to start with?
Well, yeah, that's pretty much all the communication for a submarine is going to be pretty much in that range. And the reason is because that's the only thing with propagation through seawater. So what was used to be called Project Sanguine in Upper Michigan and I think Wisconsin, they had these huge long wire antennas, just hundreds of miles long. pumping gobs of power into this at 200 hertz, and all the environmentalists are worried they're cooking the earthworms, you know. So plus it's also highly inefficient. So one of the things that HARP did, and other sites like HARP, HARP was not the first one to experiment with it. The Russians were playing around with it as well. Is again going to the auroral oval, the thing that we don't like to have to contend with as radio amateurs. The auroral oval has what's called an electrojet. It's actually a circulating electromagnetic, well, basically a circulating electric field that's excited by the sun. Well, what happens is it's nonlinear. So we can take two HF signals, which you can generate pretty efficiently, and separate them by 200 hertz. So we pump the ionosphere with two radio signals separated by, let's say, 200 hertz. What do we know about any nonlinear device that you put two signals into it?
You get the sum and difference out.
Very good. Okay, so we relied on the ionosphere itself to give you the difference frequency. Now, the sum frequency wasn't too useful, but the difference was. So by using, rather than having to use antennas that are hundreds of miles long, we used HF antennas in the 4 megahertz range, 4 to 5 megahertz range, and separated by 200 hertz, and then let the ionosphere do the rest of the work. Well, another interesting thing about it, since the ionosphere, or the region that was modulated with HARP, is a circular region, it is a closed loop transformer. This gave a very efficient coupling to the submarines under the ground. Now, since it's pure magnetic coupling, it's not really electromagnetic. Electromagnetic wave is, you actually have an E and M wave that are separate. Whereas you have a transformer, you have basically you're only working with a near field, a pure magnetic field. So the issue was never fully resolved. Is this ELF communication actually electromagnetic, or is this strictly magnetic coupling? So that can make a little difference. One of the things that we can do is the electromagnetic field, attenuates. If you move away from an antenna, how does the field decrease in terms of distance? Does 1 over R squared sound familiar? You double the distance, the signal goes down in half. The near field pretty much tapers off linearly. So the near field has a very restricted range that it can go out. Whereas the EM field goes on forever and ever, and it propagates itself. So that's one of the main doctrines of electromagnetic propagation is you have these two fields at right angles, and they propagate upon each other. They carry each other by their own bootstraps. So anyway, some really interesting stuff. I'm working with a really low frequency like that. Now, you don't have to be quite extreme if we're working at 2,200 meters or so, but a lot of the same techniques are used for that. It's unexplored territory. We don't know really what effect the D layer has on 2,200 meters, and that's one of the things that we can actually actively contribute as radio amateurs to the state of the radio art.
There was a discussion last night that I was on, and they were talking about using 2220 for use following an EMP type of event because of the fact that they wouldn't be dependent on the ionized propagation. Yeah,
that's true, and that's a lot of the ELF submarine communication the same way. It'd be not very much affected by the ionosphere itself. And again, the lower frequency you go, less the losses are at ground wave propagation. You actually have true ground wave propagation at low frequency. So we can, the AM broadcasters have known that forever. And, the NBB guys, non-directional beacons used at every airport since the dark ages, rely on ground wave propagation for that. Let's see here. So we have the ionosondes, which are extremely useful. Again, I rely on ionosondes almost exclusive. For kind of a general idea, I look at the solar indices and say, okay, well, this is what it should be. But again, the solar indices are pretty much a very broad brush. So they tell you what's supposed to happen, and they tell you what's going to happen kind of on a worldwide basis, but they won't narrow things down for you locally. And by locally, I mean two different locations or two different terminations of where you want to talk to. Now, we can talk a little bit about gray line propagation. How many actively pursue gray line propagation?
160, yes.
Now, an interesting thing about gray line propagation in Alaska, we have some great gray line propagation, except there's nobody at the other end of the line. During the middle of winter, if you look at the gray line, is exactly horizontal. So they can aim either directly east or west, but there's nobody at the other end of the gray line, so it doesn't do us much good there. So it's kind of it's out in the middle of South Atlantic someplace. But the gray line gives you a lot of insight because it shows you that the ionosphere ionizes a lot quicker than it deionizes. Is generally, if we look at the ionization level and the electron density profile as we go from morning to noon, it pretty much increases linearly. But after noon, after everything goes up, there's a lot of afterglow. This is why, 80 meters, which theoretically you think would totally go away after the sun goes down, has some of its best propagation. Anybody ever played around with what you're pretty sure is chordal Hop propagation? An 80 or 160? Chordal Hop propagation is when you have multiple reflections off the ionosphere without the intermediate reflection off the ground in between. Most are multi-hop propagation, goes up the ionosphere, comes down, bounces off the earth, back up and down. Well, if the ionosphere is high enough, and again, we mentioned that the ionosphere after nighttime contracts from the bottom up, the ionosphere becomes very high. So what we can have, if we launch a low angle radiated signal, it can bounce off the ionosphere and then bounce off another section of the ionosphere further around orbit. And multi-hop, chordal hop propagation is extremely low loss. The Earth is a pretty lousy conductor, so the propagation or bouncing that we have off the Earth is highly lossy. But chordal hop propagation, almost for sure, that's what's coming in place. If you hear a signal that's just a whole lot stronger than it should be. And that's because you are absorbing anything in between. Now, here's something for some speculation. And I should say it can be reproduced in a laboratory, but whether the conditions exist in the wild to do it or not are still unknown. There's a phenomenon called parametric amplification. And the parametric amplification is a process where a plasma, and we know that the ionosphere is a plasma, can actually amplify a signal under the right conditions. You need a magnetic field, you need a very rapid gradient of density in the ionosphere, and you can actually amplify radio signals. Now, a lot of things have to come together in order for us to have radio amplification occur naturally. But it is certainly theoretically possible, and it's a phenomenon that's done all the time in plasma chambers. Another one is long delayed echoes. Anybody here ever experienced long delayed echoes? Or worked with anybody who claimed to have heard long delayed echoes? Well,
Many years. Go ahead.
Yeah, well, they're a phenomenon that has been observed ever since, the old ship's radio operators back in the turn of the last century. Most of them had reported some incidents of that, where, especially in CW, would be sending a signal there and hear their own signal back 10 or 15 seconds later. And all sorts of speculation, since a radio signal goes around the Earth 7 times in a second, it'd have to go around like 100 times to have that kind of delay. Or there's been speculations that the reflections from the Van Allen belts, or all sorts of really wild speculation on how that might happen. Anybody have a possible, a guess on what might cause long delayed echoes of that length of time? Well, there's a phenomenon known as, again, this is easily reproducible in the plasma chamber. It's called ion acoustic waves. Now we know that sound is propagated by simply bouncing air molecules off each other. So we have a pressure wave that goes through sound, and that's why we hear things. And sound travels around 700 feet per second. If we get up to really high, 1,100 feet per second, get up to really high atmosphere, stratosphere, it can go maybe 10 times as fast, but it's still very, very slow compared to the speed of light. However, if you have an ionized region of space, you have what's called ion acoustic waves, which is actually a mixture between acoustic waves and electromagnetic waves. What you have is these ions that, since they're heavy, they propagate very much like sound, except since they're magnetically or they're electrically charged, these waves can now generate radio wave signals with very long delays in them. So we wobble some ions in one part of the ionosphere. Those create a sound wave that propagates very slowly relative to anything else we're familiar with. And then when they get to the end, they re-wobble some, since they are electrically charged, they generate a radio signal at the far end. So it's like a huge reverb spring. Now, this is one of the, again, nobody's been able to confirm this other than the fact that they can do this regularly in plasma chambers. But it's quite possible we've had the ingredients necessary to create long distance, long delayed echoes of the ionosphere using a phenomenon called ion acoustic waves. So plasma is an interesting material. And most of the universe is made of plasma. So why it's so fascinating for us playing with the ionosphere is because it's a model of what most of the universe is made, except very close in our backyard, So very few things that you can do to get into that kind of science geeky stuff outside of amateur radio, so we can all play with them. And that brings me up to my next point. I didn't plan on doing this, but I have a new book coming out from CQ magazine. I don't have the publication yet, but it's called Playing with Meteors, and talks about all the science geeky stuff that we can do as radio amateurs. But it's pretty much geared toward newcomers into the hobby that don't have a clue what ham radio is. And so it's a real fun book, and lots of humor in it. And I think it'll be a lot of fun when that comes out. So I've been seeing this, let's see, pretty much the same 4 people have been asking questions here. Maybe we should, at this time, we have about 12 minutes left. Why don't we go around the entire loop here and take questions from everybody on anything that I might not have covered. Does that work for you?
Yes. So please go ahead and just either raise your hand or unmute.
Yeah.
Question here. It appears your book, Propagation Radio Science, is currently out of print. Any chance it'll be back in print, or do I need to start dogging the local libraries?
That's a good question. I have to get with AWL and find out. I have a few copies of my own here, but yeah, you might check with Amazon. I think so. There might be some overflow that ended up on Amazon. So yeah, I can't answer that definitively right now.
For the X and O propagation, would a vertical or inverted V be better than a Yagi for taking advantage of that?
Well, I would think it will certainly be a lot easier to put up. Again, most of the hams that I've talked to that have done anything with it all are simply doing it experimentally. So I would certainly, just to get a feel for the difference between X and O propagation, a crossed inverted V is probably the way to go. And they pretty well work whether you've got high angle signals coming in or low angle signals. Seem to be pretty non-discriminating in that regard. It'd probably take quite a bit more twiddling to build a decent X and O type Yagi, not to mention the huge amount of sky you'd take up there.
I was thinking that using a vertical, you wouldn't have the problem of which way to point that you do with the Yagi to take advantage to see which wave you're receiving.
Yeah, well, I think an inverted V is a good compromise between a vertical and a dipole. What's really interesting, if you take a cross dipole at precisely right angles, and feed them 90 degrees out of phase electrically, what you have is a horizontally polarized antenna that's omnidirectional. And this is how FM and TV broadcast stations create omnidirectional signals. But it's circularly polarized to signals coming straight down. Well, one of the interesting things about circular polarization is it gets rid of one of the ambiguities we have. In other words, if we have a circularly polarized signal coming in and we want to determine the direction of arrival, we really can't know that unless we know that we're the same polarization. However, if you do have a circularly polarized antenna, what you can do is you steer your antenna so that the signal that you have is as circular as you can get. And this is easy to do with an oscilloscope in an X and Y mode. You take a dipole, go to one channel, take another dipole across and go to the other channel. And when you steer that antenna, when you have a perfect circle, that way you know that you're on bore site. So that's one of the interesting things you have. If you have a linear polarized signal, obviously it's very easy to tell which direction it's coming from. But if it is circularly polarized, unless you also have a circularly polarized antenna, it's rather difficult to determine the direction of arrival. So you really want to do both. You want to be able to see both the polarization and you want to see the direction of arrival. So a lot of neat little tricks we can do. One of the things that I'm working with a couple of friends here is to build a polar emitter, which is just basically a receiving cross-polarized antenna using two SDR receivers that are driven 90 degrees out of phase. Now we know that SDR receivers already have an I and Q channel. So if we take those two channels and run one antenna, one to the other, right off the bat, you have a nice CPOL polar emitter, which is a pretty useful device here for, at least for radio science. It may not be of real interest to contesting or whatever, but a lot of the radio science that I do doesn't have a practical application yet. But the more we know about it, the more we can maybe apply it later. And again, because of the fact that we've gotten by for so long, pretty much a century, without knowing anything about X and O modes at all, at least the average ham, really testifies to how forgiving radio is. Next. No. Sound one hand clapping out there. I guess I answered everything thoroughly, huh?
I had one question about when you have the stacking. When you start getting up to the third and fourth and even a fifth set I've seen on some of them, what is that inferring that you're getting that large amount of stacking?
Yeah, well, that simply tells you the absorption is very low. So if they're relatively low power, you're just getting multiple reflections here. So that means basically you don't have much D-layer absorption at all. So
that's a good indicator that the D-layer absorption is down. So that would be typically what you would see at nighttime.
That's right, or ideal conditions. If you see that during broad daylight in the year, that's when you want to get on the air and hopping. Now, I had another point I want to bring up about there is, well, it'll come back to me. The D-layer absorption again is pretty much on. Oh, that's what I was saying. When you see an ionoson that's totally blank, two conditions can cause that. Number one is no ionization, right? If you don't have any ionosphere, you aren't going to see any reflections at all. Or total absorption. Well, what causes total absorption? Very high ionization. For example, if we had a coronal mass ejection or we have a lot of hard X-rays coming in, we can have very high levels of absorption in the D-layer. Well, how do you know which it is? Because two opposite extremes will cause the same condition. No ionization or such high ionization that everything's absorbed. So how do we know that? Well, the only way to do it is topside sounding. Again, we can't do that typically. But if we had a sounder overhead and we shot down, we could tell because we don't have to go through the D-layer to get to that. So whenever you see an ionoson that's non-existent, it can be one of two conditions. Now, I think most of the time that we see here is just due to lack of ionization at this point in the sunspot cycle. Again, last week we had a coronal mass ejection, which also caused pretty much a total polar cap absorption event. I hate to use the word event. An event signifies that something happens and it's done with. In Alaska, polar absorption is not an event, it's a continual state of being. So anyway.
The reason why I was asking here, because I'm looking at the ionogram from today from Millstone Hill, and I have 5 sets stacked this afternoon,
Oh, that's wonderful.
and
Yeah.
almost in the 3,000 MUF was 20.
Oh, good. 15 is gonna be wide open, and
It was. This is from a few hours back, but that's what it was like today.
oh, great, excellent. Yeah, well, enjoy it. All I can say is take advantage of it.
Does the number of ground reflections that you see on the thing indicate the level of the absorption that's occurring?
Yes, it does. Yes, it does. So you don't have to go through that delayer to get to the first reflection. I've seen as many as 6 reflections. Now it's very unusual, but and it can depend on what the ground conductivity is. Obviously, if you had an ionosonde over the ocean, you'd see a lot more of that. You got pretty much perfect reflection there. So your ground conductivity has a lot to do with things that they are. I don't know what the ground conductivity is in your bailiwick. It's probably pretty decent. Here in interior Alaska, our ground conductivity is about 4 decimal places to the worst, to the left of the worst propagation in the central continent. So we, what that allows us to do is you can lay an 80-meter dipole right on the ground and it doesn't make any difference because you're pretty much sitting on top of a glacial lens. So in some ways, having really bad ground conductivity is almost as good as having really good conductivity. Because you basically it's like an antenna lying in the ground. It's like it's 60 feet up in the air anyway. The true ground reflection is way down there.
Early in your presentation, Eric, you surprised me by indicating that, or telling me that sunspots are a measure, but not the cause of UV from the sun. We know that there's significant variation in what they call the 11-year cycle. What causes that UV? Again, I thought it was sunspots up until now. I'm just kind of curious to learn more about what I didn't know.
Yeah, the magnetic flux of the sun itself, you have it's a liquid, and you have stuff moving around that creates magnetic fields, both the motion of the fluid that the sun's made out of, and most of it's mostly hydrogen that gets converted into helium, but we have a lot of intermediate elements in between. But if we look at it as just being a ball of very hot liquid, it's very malleable and floating around there, and the sunspots are really, I guess you can call them like backfirings. They're cold spots of the sun where you don't have complete combustion there, and then it becomes very unstable. So you have a big warp. That's why you get coronal mass ejection sometimes. Is you have this unburned or unconsumed hydrogen and other particles that get ejected from the sun. Again, the coronal mass ejections are highly directional. Again, the one that came in last week was we were right on the target. We were right down the barrel of the thing. Whereas you'd see all the coronal mass ejections that shoot off into space someplace, and they miss us by astronomical units. So again, yeah, the sunspots are, I don't want to get the impression they aren't important, but again, they aren't what generate the UV. The UV is pretty much uniformly generated around the sun there. So there's a lot we don't know about that in general, but we know the correlation. We know the correlation between sunspot activity and UV. But again, the sun rotates itself, and when there's a lot of sunspots on the backside, we still get good propagation, even though they aren't aimed at us. So that's a pretty strong indication that they are indicators and not the prime movers. That make sense?
Yes, thank you.
So what happens when there's a solar flare and we lose propagation?
Well, primarily, you get charged particles coming in. Again, we want waves coming, we want rays coming in, which are ultraviolet rays, which are travel at the speed of light. When we get charged particles in, we get heavy particles like protons and sometimes a little heavier stuff. Mainly it's protons, which are massive objects. Again, protons are a whole lot heavier than electrons. And when these come in, what they do is they create turbulence in the ionosphere. So rather than having a nice smooth ionized area, it is just just huge amounts of turbulence. So we no longer have a nice smooth layer to bounce things off of. And until that clears up, then all the ripples fill in, and now you have a nice smooth surface. So a lot of it's just plain geometry. If we look at a layer of electrons, or close to a layer of electrons, the smoother that is, the better propagation is going to be. We don't want a bunch of holes and a bunch of turbulence and a bunch of virtual tornadoes happening there. And that's what happens when we have charged particles. They come in and they wreak havoc in the ionosphere. So waves are good, particles are bad. Now, the thing is, the waves, they travel, it's about 8 minutes between the sun and us. Whereas the heavy particles, it could be days to weeks to get to us. So we have a little more warning that those coronal mass ejections are going to be experienced here on Earth than the waves, which are almost immediate.
That's too much of a good thing.
Yeah, that's right. That's right. Yeah, well, it's too much of the wrong thing. So, and again, we really want what's called UVB rays, do most active. Even though X-rays are also rays, they tend to create a lot of activity in the E layer or D layer absorption. So we don't want that either. So there's a balance there. And it could be, as we showed it earlier, how thin the ionosphere is. It should be pretty apparent that it's a pretty delicate balance. The fact that radio works at all is still pretty amazing. Anybody else?
I'm sorry. When you were talking about dipoles at 90 degrees and driving them,
Right.
You reminded me of something I haven't put up yet that I had here in the shack that I brought over. But basically, were you not describing a turnstile antenna?
Absolutely. Yep.
This one's for 440.
Yeah. Very nice. You built that from scratch?
Actually, it was a kit.
Oh, okay. Yeah.
It's turned out pretty nicely. I just haven't got it up yet. It's one of the things I worked on this winter.
Yeah. Oh, very nice. Very nice. So anyway, yeah, we have a lot of radio to play with, and we have a huge amount of spectrum, and relatively little of it gets used. So I highly encourage you to start exploring stuff from DC to daylight if you haven't done it so far.
Well, I did get an IC 9700 recently, and that's got a band that I really don't have much experience with, but 1.2 gigahertz. But I would assume space communications probably its best application as far as I can see.
Oh, absolutely. We're doing moon bounce. Anybody here doing moon bounce? I've not done it directly. I've helped here that were quite into that. So anyway, that's actually a very good band for moon bounce. It's high enough that you can get some pretty high gain antennas without too much work, and low enough that it's not a real problem getting the constant kind of receiver sensitivity that you need. Any more? Any further?
This may not be very relevant to the meeting, but I'm just curious how many times you've contacted the lower 48 states, specifically the Eastern on 6 meter.
Yeah, I don't do a lot of activity on 6 meters. If I know that there's going to be sporadic E coming in, I work lower 48 all the time. It's just not the same schedule that you would have down there. So it's still, we can still shoot underneath the Auroral Oval and get there. It's just on the average, it's just a lot harder to do. But there's very few places I haven't worked. I haven't actively pursued the XCC, but I probably have it just by default. So it's just a matter of being on the air a lot of time, So, and being around when it happens. There's no substitute for just being on the air a lot and listening. So, but we're here. we have more hams per capita in Alaska than any other place in the country, you know, just a lot of people don't realize it. So I remember we had a fantastic opening back in 1988, and I worked WAS twice in about an hour. First I did on sideband, and then I did it on AM. So I started calling directional CQs there, and it was just unbelievable. And then it lasted for about a week like that, and then it went down to, you know, pretty normal stuff. But I talked to these old timers and said, well, I've been on the air for 40 years, never heard an Alaskan station. So I don't know what the deal is. We're here. We're here. And
Did you ever talk any Aurora bounce up there?
oh yeah, it's matter of fact.
That should be fairly easy, I would think.
Yeah, no, it doesn't always work for you, but we can, you can hear the aurora flutter on during winter almost all the time. You get some aurora flutter. And those people don't realize is the aurora's there all the time, whether you see it or not. Now we used to, with our auroral radar and that sort of thing, you can see how rapid it is. But it's not strictly a wintertime phenomenon. It's just during wintertime is when we actually see it. So we get a lot of, they can happen anytime. And again, the aurora is probably or primarily caused by heavy particles coming in. So generally the conditions that cause aurora are usually detrimental to radio. In general. Now we can, there's a phenomenon called field aligned irregularities where you can actually bounce VHF signal off the magnetic field lines, which accompany aurora. So, okay.
Well, thank you very much, Eric. We really appreciate you talking to us this evening.
Yeah, well, it's always fun.
I learned a lot this evening. I'm going to be studying the ionograms a lot more in the future here. And it's sort of fun. I went back through some of my log while we were on just to look at some of those days that we saw with the high sporadic E, and it was great to see the correlation.
Yeah, absolutely. And again, all these tools are free. You know, remember when I first started working on high pass, we had access to a few Digisons, but they were paid sites. We had to have special anointing to get into them. Now they're all on the air and free, and you know, you have to be a member of NSF or anything like that. So,
well, by the way, if you haven't noticed, everyone, I put in the chat some links to the ionograms for the Millstones Hill, which appears to be the best one to choose for us, I think. So there's links there, and you can back up and go to different years or different days if you want to.
For some reason, Anthony, those don't seem to be working for me, but I'll worry about it later.
Okay, I can email them to you too.
Yeah, I look at Wallops Island and Boulder and do a comparison between the two quite often.
Well, I'm going to go ahead and stop the recording. And Eric, if you could hand back the hosting, you're welcome to hang around if you want to. And